Okay. So having a double bond, or being an allylic alkyl halide, makes it more reactive.
What about if it's a vanillic?
Oh, like this?
Yeah.
I don't know if that makes it less reactive. It doesn't really touch that, but
Okay, so
it's not going to be stabilized by the conjugated system. And really, this is one of like the points like would be on the MCAT is knowing, oh, something's in the allylic position. That's probably where the chemistry is going to occur. That's why I didn't review this second semester of OChem before doing the MCAT, but if you just know, like, oh, that's probably more likely to be reactive. Same with SN2. If I have my alkyl halide here, and then I have a double bond there, if I'm going to put a nucleophile in there, that's going to be more reactive for an SN2 than if there isn't a double bond.
Okay.
The reaction will be more reactive. Another thing the book points out is if we have this secondary guy here, and we were adding, say, cyanide to it, it's more like, it's going to be SN2, most likely. But if we have the double bond here, this reaction, SN1 is now even more favorable than it was without the double bond. SN1 is not necessarily has a greater percentage than SN2 in this case, but SN1 on the allylic is more likely than SN1 without it being allylic, if that makes sense. Because even without this double bond, there's still a chance that this reaction will go SN1. But if we throw the double bond in there, the chance of it going SN1 is increased. Same with it being tertiary. Usually if we see a tertiary alkyl halide, we're reacting with an anionic nucleophile. We're assuming it's going to be an E2 reaction. Or there's a chance it might go SN1, but if we put the double bond there, the percentage of it, the product being SN1 will increase.
So whenever it's a allylic substitution, the chances of it being going SN1
Increase.
Mm-hmm. Okay.
And if anything, you can say that this is more reactive than there not being, double bond there. So really, having that double bond there, it really kind of what they've done with chapter 10 is they reviewed chapter 4, just right there, chapter 4, kind of chapter 8. Like, all right, if there's an allylic double bond, how does that affect our reactions from chapter 4? How does it affect SN1, SN2? That's what they did at the beginning of the chapter. And they also did it with like your radical deal. If you're going to make that hydrogen, if you're going to make a free radical here, that having a double bond there makes it more likely than, say, if you had this guy there. So reacting it with Cl2 and light. We'll do the same thing down here. This one is more reactive because there's an allylic hydrogen that can be stabilized by the double bond.
So allylic hydrogens are more reactive.
Yeah. And another way you can say is they're more acidic. This one has a pKa, this hydrogen here has a pKa of 63. This one has a pKa of like 43. So it's even more likely to be deprotonated and more likely to be radicalized. I don't know what that term means. So then, that's again in a review of chapter 4, that free radical addition. They also bring in how you can use NDS to put a bromine there.
Oh yeah.
Because using Br2 and light, there's a chance Br2 might react to the double bond, put 2 bromines off the double bond. So if you use NDS, it increases your odds of getting your halide. on the allylic carbon.
And so that essentially adds, well, can we also say that it's just the anti-Markovnikov?
If you want to think of it that way, yeah. Anti-Markovnikov is if you react on the double bond and you get the bromine in the least substituted position off of the double bond. Here it's more you're putting it in the allylic position related to the double bond. That makes sense. And then the book goes over really then a review of chapter 5, dealing with elimination. So if we have an OH group there and we want to form another double bond, they're going to use KHSO4 with heat.
Yeah, you do the weak bases, don't you? Because if you do a strong base, can it like start ripping everything off?
Yeah, because again, like these hydrogen, you have other hydrogens that are more acidic. In this case, I think, at least I remember this, whether it's not the case, if I were to use H2SO4, which is the normal way to eliminate an alcohol, H2SO4 might react with the double bond to put a water off of, or put an alcohol off the double bond. And if it's a halide, usually you use a strong base like sodium ethoxide, but you still use a pretty strong base. You can use KOH, and that will give you your double bond.
Now, could you use KOH on the alcohol as well?
No. Because this one you're using more of an acid to deprotonate it.
Okay. So
HSO4 is still a strong acid, just not as strong as H2SO4.
Or, yeah, that's what I meant, HSO4. Instead of the H2SO4.
Yeah. So you're using HSO4 here.
Okay, so use HSO4 on alcohols and then potassium hydroxide on halides.
But didn't he
chlorine
teach
as well.
you like that carbonate one?
Not really. The one, when we had the test review with him, he just said when forming a conjugated alkene, use the weakest base possible, either HSO4 or KOH.
Okay. So you can use HSO4 here.
I don't know.
I think HSO4 is this
For
guy,
alcohols.
then OH here. It's just how the book goes over. So that's a review of chapter 5.